of maths. In today's video, we will compute a difficult integral, namely this integral. We will give its value, and what is particular about this integral is that it cannot be computed using the calculus classical techniques. So we need something new, and what we will use is Cauchy residue theorem. So it will be the occasion to review Cauchy residue theorem and to see how we can apply it to compute integral in this form. I recall the definition of the hyperbolic cosine and hyperbolic sine. The hyperbolic cosine is just the even part of the exponential, and the hyperbolic sine is just the odd part of the exponential. So let's go. I start by recalling some facts about the essential about holomorphic function. An holomorphic function is a function defined on an open set in C, such that for any z0 in this open set, this quantity have a limit, which means that we have the C derivative in any point of z0. So f is if there is derivable or differentiable in the sense of C. So we have this definition. What we have down here, we have just taken the definition of the derivative in the real case and apply it to the complex case. But what is important is that we will get results which are totally different from the real case. Namely, we get that being holomorphic on an open set is equivalent to being analytic. So a function is holomorphic C near any point in its domain. It can be, it has a Taylor expansion near this point. And moreover, here the disk of radius r, and moreover we can compute this coefficient by this beautiful formula. So an is which is actually the n derivative a over factorial n, and it is equal to this formula. Here we have the complex integral over the circle of center A and radius r, positively oriented. And the definition of the complex integral is given by this formula. If you want to integrate a complex function on a curve in the C plane, you need to give this curve a parametrization and use this formula. So with gamma t, which is equal xt yt, you have this complex integral is equal to the integral from a to b g gamma t gamma prime t dt. Okay, now for the Cauchy's residue theorem, we need to introduce a class more general than holomorphic function, and they are meromorphic function. A meromorphic function on an open set is a function defined on this open set except a set of isolated point, and it is holomorphic on this set. And moreover, for any point in this set, the function is equivalent near this point is equivalent to L over Z minus A power M. So for any A in this set, which is the set of singularities of this function, the function is equivalent to L over Z minus A power M. And the element of this set P are called the pole of F. So, roughly speaking, a meromorphic function is a function which is holomorphic on an open set, except a set of isolated points, and near any point, any singularity, this singularity can be controlled in this sense. F is equivalent to L over Z minus E power M. Of course, any holomorphic function is meromorphic because in this case this set is just empty. Now, one of important property of meromorphic function, as holomorphic function, we have seen that a holomorphic function is analytic and near any point has Laurent expansion. Meromorphic function have also an expansion near any singularity given by Laurent expansion. So if you take a singularity, a point, and a disk near this point, and then F has a Laurent expansion. This Laurent expansion has this form. You have this regular part, and the singularity are given by this formula. So meromorphic function are functions which have singularities, but singularity which we can control. And here M is the order of the pole A. If you take this function exponential 1 over Z, you see that it has a Laurent expansion, but the Laurent expansion goes to minus infinity. So here, near this function is clear. It's holomorphic on C star, but near the singularity explodes. We cannot control it because it goes to infinity, and it is an example of a function which is holomorphic except on one point, but it's not meromorphic. Now let's give an important property of a meromorphic function. So we take a meromorphic function, we take a singularity, and we write its Laurent expansion. Now we take a circle centered at the singularity of radius small r, and we give this circle of parametrization. This is the standard parametrization of a circle, and we compute this complex integral. So here we must, so we get gamma t minus a. Gamma t minus a is just t, power p, so we get this quantity. Now the derivative of gamma t is ri exponential it, and we get this quantity. Now, so we have shown that this complex integral is equal to this one. Now, as we can see, if p plus 1 is different from 0, this function has a periodic antiderivative, which is 1 over pi plus 1i, exponential pi, and this, in this case, this integral vanish. The case when p equal to minus 1, here we get 1, and we get y 2 pi, and we get this formula, this beautiful formula. So now, if we apply this integral to our function, we get this beautiful formula. It is the first residue formula. Here, this coefficient appear, and this coefficient is the residue of f at a. We call it c minus 1 is the residue of f at a. So what we have done, we consider the meromorphic function. We consider its Laurent expansion near a singularity E, and we define this coefficient as the radius of A in A. And we have this beautiful formula. Now, if we multiply our function by z minus a power m, we get here an allomorphic function, because we have no more quotient by z minus a, and we have shown that fz is the quotient of this allomorphic function by this allomorphic function. And we can see that to compute this coefficient, we need to take the consecutive derivative of this function, and we get this beautiful formula for the residue of f at a. So the residue of f at a is 1 over m minus 1 factorial, the m minus 1 derivative of z minus a m fc. And now what is important about this formula is that we don't need the Laurent's expansion of f to compute the residue of f at a. Okay, now we consider the case which appear in all the concrete situation. Your meromorphic function is actually the quotient of two allomorphic functions. We have seen that it's the case locally, but now we have this situation globally. So you take a meromorphic function, which is the quotient of two allomorphic functions. You take a zero of h, a which satisfy he equal to 0 and ge different from 0. Since h is allomorphic and ha equal to 0, in the Taylor expansion of h, you can make some z minus a m as a factor or holomorphic function, and we get this situation. So now a now is a pole of f of order m, and its residue is given by this formula gz over h1z, and here it is useful, and it's what we will use in the concrete situation. And in the case where the pole is simple, this means that its order is equal to 1, the residue is equal to G1A-1, and sometimes you don't need to have H1. You can use this formula GAH', because when we take the limit of z minus a f z, you get this formula. And we have, now we can apply these two formulas in concrete situation. So the first one, we take this function. This function has two sample poles, I and minus I, and the residues at I is just this value, and the derivative of this function to I, and we get this. And the same thing happened for minus A, and we have the residue easily. Recall that cosine h is given by this formula. And in the case where the order is bigger than 1, we take this example. So here we have two poles of order 2, I and minus I, and of course we need to compute the derivative of z minus a 2 fz, and we get, so we need for I, we need to compute this derivative, so we compute as classical derivative. The derivative is exponential, so we get this formula, and we do the same for minus I, and we can compute now the residue of this function in I and minus I. Now we have seen what is a meromorphic function and how we can compute the residue of its poles. Now we can give the Cauchy residue theorem. So Cauchy residue theorem tells us that if when we have a meromorphic function on a domain U in C, a curve which is positively oriented, simple and closed in U, and inside this curve there are n poles. So the theorem, so we have the situation now, we have the domain U, we have the curve gamma, and we have the poles. And the theorem tells us that the complex integral of the function f along this contour is equal to pi I, the sum of the residue lying inside these curves. So we have this beautiful theorem. And what we will do now, we will see how we can use this theorem to compute. So here, what you need to compute this integral, what you need is just to compute the residue of f at the poles inside this curve. Now, this theorem can be used to determine integral of this form. So the method, we extend this our function to a meromorphic function on C or on a part of C. We choose an appropriate contour which is parameterized by R, and R will go to the infinity, and we choose this contour such that the limit when r goes to infinity of this integral is equal to this integral. Now, by using Cauchy residue theorem, this quantity is equal to 2 pi I, the sum of residue. So we get here the constant equal to this integral, and we get what we need. To be honest, this theorem is powerful, but the most difficult part is to choose this curve. And the only way to become familiar with this is to study many concrete case. Let's apply this method to our example. So we will compute this integral using the method derived from Cauchy's residue theorem. First, so we consider this expansion of our function, of this function to C, and here this part is the real part of this one. So we have that our integral is 1 over 2, the real part of this integral, because this function is even, and the integral from minus infinity to infinity is equal to 2 times the integral from 0 to infinity, and we have this. So now we will apply our method to this function. So we need to determine the poles of this function. We need to define an appropriate contour, and with this we need to see what are the poles lying inside this contour, and we will apply Cauchy's residue theorem. So let's go. First, the poles of f. The poles of f is the value of z which annihilate this quantity. So we must solve this equation. Cosine hyperbolic z plus cosine hyperbolic a equal to 0. Now cosine hyperbolic z is just exponential z plus exponential minus z over 2. We multiply by 2 and we get this equation. Now this is 1 over az. We multiply also by az, and we get that az satisfies this equation. So we need to solve this equation. It's an easy one. So we compute its discriminant, and we use the useful formula cosine hyperbolic 2 minus sine hyperbolic power 2 is equal to 1, and we get the solution of this equation. X equal minus a exponential a, or x equal minus exponential minus a. Now we have that z is a pole if and only if az equal to this one or az equal to this one, and we transform these two equations by writing that minus 1 is exponential ep, and now a z minus a equal e I pi. This means that z minus e is equal to I pi plus 2k pi, and we get the poles. So we have the set of poles of f. Okay, so now we have the poles. Now the contour, we take this contour, this curve which goes from minus r to r, and then from r to r plus 2ip, from r plus 2ip to minus r plus 2ip. So it's our contour, it's this closed curve. Now we have that we take r bigger than a, because we can do so since r at the end will go to the infinity, and inside this contour we have two poles, a plus ip and minus a plus ip. So now we have the poles, the contours, the poles inside this contour. Now we need to apply Cauchy's residue theorem, so we need to parameterize these curves. So we have four parameterization. We have this first curve, so its parameterization is gamma 1t equal t for t between minus r and r. Gamma 2t, this one, is r plus it for t between 0 and 2 pi. Gamma 3 is minus t plus 2 ipt, this one and this one. It's easy, and we have, so now we have the poles, the contour. Let's compute, let's apply the Cauchy residue theorem. So the Cauchy residue theorem tells us that the sum of the complex integral of f over the four components of our contour is equal to pi r, the residue of the poles inside our contour. And now we use this formula to compute this complex integral. So the first one is just since gamma 1 t, by using this formula we get this one. For the second, for gamma 3, we get gamma 3 is equal to, so we get this formula. And now we can see that if we replace t by minus t in this integral, we get the same thing, and we get, by a change of variable, we get this formula. So we have, now we have, and what we can see that if we take r to infinity, we get the integral we are looking for. Now for the other two complex integral, gamma 2 and gamma 4, we replace by using this formula, and we get this quantity. Now we will show that actually these two integral goes to 0 when r goes to the infinity. So we will show this formula. To do so, we need to give a majoration of this function. Here this quantity is less or equal in module is less or equal to 1, so we need to get a majoration of 1 over this quantity, so we need to give a minoration of this quantity. So let's go. First, remark that cosine hyperbolic r plus it is equal to this quantity. So if you take 1 over 2 exponential r, it is equal to this quantity, because here we simplify by this term, we simplify, and the module of it is equal to 1, so we have this quantity. Now by the triangle inequality, we get this formula, and we get, so this quantity is bigger than 1 over 2 AR minus this quantity. So if we take the inverse, we get this inequality. Now by we have this one. Now we can have a majoration of our integral by this quantity, and this quantity goes to 0 when r go to infinity, because sinus hyperbolic r goes to infinity when r go to 0. And we have this. And in fact, in many situations when we apply Cauchy's residue theorem to compute integral, we are in this situation. We must show that a part of our integrals goes to 0 by using an appropriate majoration. So now we have all what we need. Here we have this quantity, we have this one. We know that for gamma 2 and gamma 4 the integral goes to 0, and so when we take r to infinity we get this formula. So our integral is equal to this quantity over this quantity. Now we need to compute the residue of f of these poles. They are simple poles, and we use the formula, and we get this quantity over the derivative here, and we use the definition of hyperbolic sign, and we get this formula, and the same for minus a plus I pi. And now we have that this quantity is equal to this. Now this quantity, we can write it like that, and here we get this equality, and we can deduce finally our formula, and we get that our integral is equal to. Okay, so we have done, and it's in my opinion it's an example where we can see how to apply Cauchy residence theorem to compute such integral. And of course, to support the channel, please like, subscribe, and share. And thank you.